Metallography Part 2. Microscopic Techniques. Metallic materials are widely used in many areas of everyday life. How are they built up internally? Are there perhaps crystals to be found? And if so, how big are they? What kinds of crystals are there? What is their shape? And are there voids or inclusions? Metallography gives an answer. In this video, we would like to introduce the microscopic techniques of metallography. Microscopic means to investigate a workpiece at higher magnification, usually with a light microscope. To have a look at the inside, the material has to be prepared properly, and this is how it is done. First of all, a small specimen has to be cut from the actual workpiece. The specimen is mounted in resin, ground in several stages, polished in several stages, and finally etched. Now the specimen is completely prepared and ready for microscopy. As a typical example, we are going to investigate a bar made from a steel used millions of times, the plain carbon steel C45E, with 0.45% of carbon. To start with, one of our material testers defines the intended sectional plane and marks it on the bar. In this case, it's a longitudinal section. Then he takes the bar to the abrasive saw to cut out a small sample. He fixes the bar securely, prepares the machine, selects the cutting parameters, and starts the first abrasive cut. Intensive water cooling and appropriate cutting parameters are important to keep the material as cool as possible. After finishing all abrasive cuts, the material tester picks up the sample and hands it over to his colleague. For further processing, the specimen has to be mounted in resin. To ensure that the resin will adhere well to the specimen surface, the specimen is placed in an ultrasonic cleaner bath for a few seconds. Alcohol and ultrasonic waves help to remove fat and loose particles from the surface. A short time under the hairdryer and the specimen is clean and dry. To mount the specimen, small plastic molds are suitable. The material tester picks up the clean specimen and carefully places it into one of the molds. The intended plane of examination is at the bottom. Then he pours liquid resin into the mold. A thin layer of grease at the inner surface of the mold acts as a release agent. This ensures that the cured resin can later be released easily from the mold. Now the mold containing the specimen goes into the light curing unit. Under the action of intense blue light, the resin polymerizes within half an hour. The resin has cured and embedded the specimen well. As an alternative to light-curing resins, many other embedding materials are available. Each of them has its own advantages and disadvantages. Because the top surface is still uneven and slightly sticky, the material tester grinds it there until it is even. He uses a rotating water-lubricated disc equipped with coarse-grained silicon carbide paper. The circumferential surface is slightly ground as well to ensure a clean specimen. Now comes the most important part, the preparation of the intended plane of examination. Our material tester begins with comparatively coarse 180 grit abrasive paper. He makes sure to press the specimen calmly and evenly onto the abrasive paper, compensating the tendency for the sample to tilt. He also makes sure not to grind his fingertips accidentally. Now he has achieved an even, relatively rough surface. The specimen is ready for the next step with finer paper. He inserts a new 320 grit abrasive paper onto the disc. Rotating the specimen by 90 degrees leads to new grinding grooves perpendicular to the old ones. In this way, the material tester can easily check whether the old grinding grooves have been removed completely. It is important to use sufficient water flushing during grinding. This keeps the sample cool and prevents the abrasive paper from being loaded with material particles. Grinding continues with 600 grit and 1000 grit abrasive paper until an immaculate, finely ground specimen has been achieved. The specimen is now ready for polishing. An absolute prerequisite for polishing is a thoroughly clean specimen. The ultrasonic bath and running water help to remove any residue from the ground surface. Otherwise, hard particles might be pressed into the polishing cloth and scratch the surface. Hands should be washed as well so that no unwanted particles find their way to the sample and the polishing cloth. Now the material tester can start with a first polishing operation. He chooses a polishing disc equipped with hard cloth of low resilience, moistens the cloth with a suitable lubricant, and adds 2 splashes of diamond suspension of particle size 6 micrometers. Under counter-rotating motion, he presses the specimen with high pressure onto the polishing cloth. The diamond particles have settled on the cloth and are now abrading the surface. After about a minute, all grinding grooves have been removed and the specimen surface already has a shiny appearance. But still there are many fine scratches to be found, resulting from the 6 micrometer diamond abrasive. To remove them, the material tester washes the specimen and his hands again very carefully and polishes the specimen for a second time. Now he uses a softer short nap polishing pad, finer diamond suspension of 3 micrometer particle size and less pressure. After the second polishing operation, the specimen surface has an almost mirror-like appearance. No more scratches can be seen with the naked eye. Nevertheless, the specimen has to be cleaned again and go through a third and final polishing operation. This time, 50 nanometer aluminium oxide abrasive is used. Only then is the surface prepared to a sufficient quality. At the end of the mechanical preparation, special care has to be taken to clean the specimen properly. On the one hand, all abrasive particles have to be removed. On the other hand, the freshly polished surface must not be scratched or damaged. Under running water, the material tester gently wipes the specimen with cotton wool, thoroughly rinses it with alcohol, and dries it with a hairdryer. From now on, the sample is called a metallographic specimen or microsection. Judged with a naked eye, our metallographic specimen seems to be well prepared. It is now allowed to go under the microscope for the first time, or rather onto the microscope. In fact, the design of typical metallographic microscopes is inverted. Inverted means upside down. The microscope objective is not facing downwards as usual, but upwards. This offers the advantage of simply placing the metallographic specimen on top of the microscope stage. The prepared surface faces downwards. Using the built-in digital camera, the polished specimen surface can be observed on the computer monitor. In the polished state, there isn't much to be seen in this material. Only some elongated non-metallic inclusions can be observed, but if these inclusions are of special interest, then the polished state is the perfect one. Inclusions may best be seen here. However, if one wants to see the crystals, the grains and grain boundaries, then the microsection has to be etched. To do this, our material tester protects himself with a lab coat, puts on safety glasses and pours the etchant into a small glass bowl. The etchant consists of a solution of 10% of concentrated nitric acid in alcohol. Now he turns on the water tap, picks up the freshly polished microsection with gripping tongs and immerses it for a few seconds into the etchant. Then he rinses the microsection thoroughly with water and afterwards with alcohol. The hairdryer is again used for drying. The excitement increases. Was the etching time correct? Has everything worked out fine? At low magnification, not much can be seen, which looks characteristic. The tester gradually switches over to higher magnification. In between, he focuses and adjusts the brightness. At medium magnification, light and dark areas become visible. At comparatively high magnification in some of the dark areas, fine stripes may be recognized. The microstructure in the darker striped regions is termed pearlite. Pearlite consists of thin alternating crystals of ferrite and cementite. The white regions are ferrite crystals. They consist of almost pure iron. Great! The etching has been successful. In a similar manner, virtually all materials of our world may be examined. This is the plain carbon steel C80 with 0.8% of carbon. Only pearlitic regions with their characteristic alternating layers of ferrite and cementite can be seen. And this is the plain carbon steel S235 after a color etching. It only has a low carbon content. The relative amount of differently colored ferrite crystals is high, the proportion of pearlite regions low. The variety of materials is huge, and each material needs its own individual preparation method in metallography. The preparation is often not conducted by hand as shown here, but by automatic methods. This saves time and money. The principle, however, is always the same: sectioning, mounting, grinding, polishing, and etching. The scanning electron microscope. Scanning electron microscopy is one of the most fascinating examination methods. This video shows how it works in practice. Main components of the microscope are column for electron beam generation, specimen chamber, vacuum pump, monitor, and control panels. The material tester turns on the vacuum pump control and vents the specimen chamber. After pressure equalization, she can open the cover plate of the specimen chamber. Together with the cover plate, the stage pans forward. Now different specimens can easily be placed on the round stage. The filament of an old used light bulb, part of a welded tube on a sample holder, a small cobalt plate, and a golden piece of jewelry. All specimens are assembled and we are ready to start. The material tester carefully closes the cover plate and switches on the two-stage high vacuum pump as well as the electronic control. It takes about 3 minutes to obtain a sufficient vacuum in the specimen chamber and column. Meanwhile, she turns on the monitor, initializes the motorized stage and boots the microscope control. Only now she is allowed to switch on the high voltage and the thermionic cathode. For the first time, a reasonable image appears on the monitor. It shows part of the specimen stage. Using the trackball, she moves the stage within the microscope. She looks for the place where the first sample is positioned, the used filament. The magnification is gradually increased. The position readjusted, and the magnification increased again. Now a plastic and high contrast image of the filament can be seen on the monitor. Originally, the coiled coil filament was quite smooth on the surface. Caused by the everyday use of the filament, new crystals have been formed. Tungsten atoms have evaporated and the outer regions of the filament have become polygonal. But how is this plastic image generated, and how does the microscope actually function internally? The animation first shows the schematic structure from the outside. The upper part is the so-called column. It is used to generate an electron beam. The lower part consists of the specimen chamber with a cover plate. In the longitudinal section, the flange leading to the high vacuum pump is visible at the bottom. Thereby, high vacuum is generated inside the whole microscope. The round specimen stage may not only be moved to the left and to the right, but likewise in all other directions. It may also be tilted and rotated. All samples to be investigated are placed on the specimen stage. To create an electron beam, a V-shaped thin tungsten wire is used, the so-called thermionic cathode. Heated up by electric current, it emits electrons into the vacuum indicated by small dots. Below the cathode, a metallic disc with a central borehole is installed, the anode. The anode is connected with a positive pole of a high-voltage source, the thermionic cathode with a negative pole. Further necessary components have been omitted for the sake of simplicity. The strong electric field between cathode and anode accelerates the electrons downwards. These electrons are called primary electrons. They form a broad, diverging beam which hits the specimens and the stage. But this way, the beam of primary electrons is not useful yet. An electromagnetic lens focuses it finely on the specimen surface. At the point of incidence, primary electrons knock out electrons of the sample material. These knocked out electrons are called secondary electrons. Additional components are necessary: electromagnetic deflection, raster scan generator, secondary electron detector, abbreviated as SE detector, and computer with monitor. The basic principle of the scanning electron microscope is to detect the secondary electrons and use them to build up an image. To increase the number of detected electrons, a positively biased grid is placed in front of the detector. The grid attracts the secondary electrons and leads them to the SE detector. And this is the way to generate a magnified image of the sample. The raster scan generator directs the electron beam to the left rear part of the sample and stops there for a short time. The number of secondary electrons is recorded in the SE detector. The signal is amplified and displayed as a dot at the top left-hand corner of the monitor. The electron beam pans slightly to the right, stops again. The measurement is repeated. In the same way, the next points on the sample are dealt with. The principle is, many recorded secondary electrons lead to a bright image point, few electrons lead to a gray image point, and none at all to a black one. An entire row is covered in this way. Then a second row, until finally a rectangular area has been scanned and an image appears on the monitor. If not only a few but many image points are used in the raster scan, a natural-looking image of the specimen surface can be seen on the monitor. Back in reality, the material tester selects low magnification again and looks for the second sample. It is an austenitic stainless steel tube with a longitudinal weld. Invisible to the naked eye, the scanning electron microscope reveals fantastic crystals. They have grown near the surface during solidification of the weld deposit. In some crystal directions, the solidification rate is particularly high and so-called dendrites form. Dendrites are crystals with many branches and tree-like shape. On the surface of the weld, they could grow almost freely without much disturbance and can now be observed well. Last in line is the golden piece of jewelry with a gemstone. The material tester is especially interested in the chemical composition of the gold material. Does the promised gold content really exist? Which other elements have been added? She chooses a place near the edge of the piece and selects a suitable magnification. Now she makes use of a fantastic method, the non-destructive chemical analysis with the scanning electron microscope. And it works like this. When the fast electrons of the electron beam, the primary electrons, reach the surface, they knock out electrons of the specimen material. These are the secondary electrons used for image formation. What happens in detail shows a schematically drawn atom from near the surface. Just like any other atom, it consists of a positively charged nucleus and negatively charged electrons. The electrons stay in energetically well-defined shells around the nucleus. A primary electron comes from above and accidentally knocks out an electron from the K-shell of the sample atom. A vacant place remains as indicated by the yellow circle. This state is unstable. An electron from the L-shell fills the gap and the energy difference is released in the form of a characteristic X-ray photon. This X-ray photon is called characteristic because its energy is quite characteristic or typical for the particular element. Now another transition follows. and finally the atom repairs itself with an electron from the vicinity, a free electron. So X-ray radiation is generated during the operation of the scanning electron microscope, namely X radiation, which is characteristic for the chemical elements present in the sample. If the energy and the intensity of the radiation are measured with an X-ray detector, then the chemical composition of the sample can be determined. Here the typical X-ray spectrum of the piece of jewelry builds up. Chemical analysis is then carried out using sophisticated methods with the help of a computer. Certain limitations must indeed be minded, but it's definitely a fine method, and above all, it is completely non-destructive, and even very small spots on a sample can be analyzed. And what has happened to the small cobalt plate, which was one of the samples? It was used to calibrate the measurement. This means to adjust it finely. The chemical analysis is finished now. Our piece of jewelry is genuine. The gold content amounts to about 70%. The balance is silver and copper.